Hi, everyone, and welcome to week 13 of Introduction to Logic. Today, we're going to be discussing conditional proof and indirect proof in predicate logic. Now, as a reminder, here are the forms for conditional proof and indirect proof. Hopefully, this should be reviewed by now from your work in Chapter 7. But if you remember, conditional proof over here on the left is when you have to prove a conditional. So if you're trying to prove some conditional like P implies Q, you can start an indented sequence assuming the antecedent of that conditional P and trying to prove Q inside the scope of that same indirect sequence. If you can do that, you can discharge the conditional proof sequence and conclude that P implies Q, citing every line in between P and Q there in the indented sequence. By contrast, indirect proof is a rule you can use much more broadly. Anytime you know you need something, you can assume the opposite of what you need. So for example, if you know you needed the negation of P, you could start out by assuming P is true, show that that leads to an explicit contradiction, something like Q and not Q, any explicit contradiction. And then you can conclude that that initial assumption has to be false, because obviously if the assumption leads to a contradiction, then that assumption has to be false. So I want to talk about the use of conditional proof and indirect proof now in predicate logic. Largely, conditional proof and indirect proof are used exactly the same way as they are in propositional logic, with the exception of one rule. There's a restriction on the use of universal generalization and how to use that correctly inside indented sequences. So here is the restriction. This is the only really new thing you have to learn in order to master the exercises for this week. There's a new restriction on universal generalization, UG. So if you're using conditional proof or indirect proof, universal generalization cannot be used in the scope of an indented sequence if the instantial variable, y, in other words, the free variable that you're using to do the universal generalization step, is free or unbounded in the first line of that sequence. So I know that's a mouthful, but I want to look at an example from your textbook about how this restriction applies. So here is a proof with a mistake in it. So again, I don't want you to think this is a correct proof. This is a proof with an invalid step in it, which I hope is really clear here from what you see on the screen. So remember, the restriction says that you can't use universal generalization, UG, right here, inside the scope of an indented sequence if the instantial variable is free on the first line of that sequence. So here the instantial variable is X. That's the variable that we are using to do the universal generalization step. And that variable is free here on line 2. It's unbounded, means it's not bound by a quantifier. And so this will result in an invalid step that does not actually follow from the assumption. And so this is just something to be wary of. This doesn't actually come up very much, but if you catch yourself trying to generalize based on a free variable inside the scope of an indented sequence, you need to check to make sure that variable is not free in the first line of that sequence, like you see here. If you see that, then you can't use universal generalization. That's really the only restriction on the use of conditional proof and indirect proof in predicate logic. And if you, like I said, if you try to use that step, you'll end up with something that doesn't actually follow, and your proof will be invalid. Let's go ahead and look at some conditional and indirect proof techniques, conditional proof and indirect proof techniques in predicate logic. So I want to look at a few examples of some proofs using predicate logic. I've actually completed these proofs for you for time's sake. I worry that these videos are getting a little unwieldy, and really there's not that much new to learn this week. It's just a matter of learning to use conditional proof and indirect proof with predicate logic while keeping that restriction in mind. So I want to talk through a few proofs, indicate what I notice when I look at the proof that would indicate how you'd go about starting the proof, and then give you plenty of time to work on your exercises for this week. So remember, you can use conditional proof anytime you're trying to prove a conditional. And here, if you look at the conclusion is a conditional. The main operator, which I'm going to highlight in blue, is this horseshoe right in the middle of the statement. So because that's a conditional, we can try to prove that using conditional proof. So what I've done here on line 2, I'm going to indicate it with an arrow. On line 2, I've assumed the antecedent of that conditional, and I'm trying to prove the consequent of that conditional. If I can do that, then I can close the conditional proof sequence and show that the conditional is true. So let me just walk you through this proof. Since we're assuming the antecedent of the conditional, we're assuming there exists some x, hx. In other words, there exists something that is an h. Now we want to go ahead and try to use our deduction rules, trying to get there exists something that's an I, the consequent of that conditional, inside the scope of that conditional proof sequence. So since line 2 is an existential statement, the main quantifier is that existential quantifier, I can use existential instantiation, but I have to use a constant that doesn't appear anywhere else in the proof. Remember, that's one of the restrictions on the use of existential instantiation from a couple of weeks ago. So here I've instantiated that statement with the lowercase letter a. So that gives us HA on line 3. From there, I can instantiate the universal statement on line 1, way up here in the one given premise, using the same instantial letter. Remember, you can instantiate a universal statement with either a constant or a variable. Here, I'm choosing the same instantial letter A, so I can apply some propositional logic rules together with line 3. So that will give me HA implies IA on line 4. From there, it should be clear that you can do modus ponens. That gives us IA. In other words, the predicate I applies to the lowercase constant a, the object referred to by that constant. From there, once we know that the lowercase letter a has the predicate I attached to it, we know that there has to exist something that is an I, and that's what we get on line 6 from an existential generalization step. So once we've obtained there exists something that's an I, we can close our conditional proof sequence, and that gives us the conclusion. If there exists something that's an H, then there exists something that's an I, and we got that by a conditional proof. So this is a fairly straightforward example of how to use conditional proof in predicate logic. It works exactly like it does in propositional logic. The key here was recognizing that the main operator, in fact, I'll use a different color so you can see it, the main operator of this conclusion that we're trying to prove is this horseshoe. That tells us that the conclusion is a conditional, so we should immediately think that we could try to prove that using conditional proof. Okay, let's look at a couple more examples. So in this argument, the conclusion is a universal statement. It says for all x, if that x is an A, then that x is a C. In English, we would say all A's or C's would be how that would be translated into English. Now, whenever you're trying to prove a universal statement, you should immediately think, well, what I can do is try to prove the form of what's inside that, that expression bound by the universal quantifier, AX implies CX, with some variable, any variable. And then you can think that you can use universal generalization to prove the universal statement. So the question then becomes, how can I get AX implies CX with a free variable? And of course, that itself is a conditional. And of course, this now you want to start thinking in terms of conditional proof and indirect proof. What we need here is a conditional. We need to prove AX implies CX with free variables so we can apply a universal generalization step and get the universal statement as the conclusion. So because what I need is a conditional, AX implies CX, I'm going to try to get that by conditional proof. I'm going to start out by assuming the antecedent, AX, and then I'm going to try to prove that I can get the consequent of that conditional, CX. I'll close off the conditional proof sequence. That will give me AX implies CX. And then finally, you can see here on line 6, I'll apply a universal generalization step to generalize and reach a universal conclusion based on the conditional that you see on line 6. So we can walk through it a little more carefully in more detail, but I want you to understand the structure of what we're doing here. Like I said, we started out by assuming the antecedent of the conditional we need, AX. ACP, assumption for conditional proof. Then I recognized I needed to do an addition step here because that will give me the antecedent to this conditional that you see inside the universal statement in line 1. So I took AX and I added BX onto it with a wedge using the addition step so that when I instantiate line 1 with a variable, which I've done on line 4, I'll already have the antecedent of that conditional. From there, you can see it's a pretty easy modus ponens step to get CX on its own line on line 5. And that's what we were looking for. We started out by assuming the antecedent of the conditional we needed, AX, trying to prove the consequent of that conditional, CX. We close our conditional proof sequence. That's what I did on line 6. That will give me the conditional AX implies CX. Now, the key here is that I needed that with free variables so I could apply universal generalization and reach a universal conclusion, a statement about everything in the universe, in other words, from what you see on line 6. But this is a really elegant use of how to use conditional proof in conjunction with universal generalization to prove a universal statement. You start out by assuming the antecedent of the conditional that you need inside the universal statement, try to prove the consequent of that conditional, close off your conditional proof sequence, and then apply universal generalization. So this is a pretty straightforward proof, but I want you to spend some time and look at this and make sure you can understand exactly why this proof works. Okay. Let's look at a slightly more complicated example. Okay, so we're given one premise. The premise is pretty complicated. It says for all x, if you have px implies px, then you can get qx implies rx. And the conclusion we're trying to prove is a universal statement. All q's are r's. In other words, for all x, if that x is a q, then that x is an r. So what I've done, I've tried to do this proof with an indirect proof sequence. I might have tried to do this using the same technique as what you saw in the previous proof, but here I wanted to do it using indirect proof so you can get an example of how indirect proof works. So what I've done, in order to try to prove the conclusion, I've assumed the opposite of the conclusion. So if I'm trying to prove that the conclusion is true, I'm going to assume that the conclusion is false. That's what I've done here on line 2. I've assumed the negation of that universal statement as an assumption for indirect proof inside in the indented sequence on line 2. Then the goal is to try to get any explicit contradiction. Remember, it has to be a substitution instance of Q and not Q. Any statement and its negation conjoined together. And you can see that I got that here on line 9. I've got PM, in other words, the constant M has the predicate P attached to it, and the negation of that statement on line 9. I can walk through this proof line by line, but I really want you to understand in broad brushstrokes what's going on in this proof. I assume that the conclusion was false. I've shown that that leads to an explicit contradiction, some statement and its negation conjoined together. Then I can close off my indirect proof sequence. That will have shown that the initial assumption is false here on line 10. In other words, it's not the case that that universal statement is false. That's why you see the double negation there on line 10. And then finally, a double negation step on line 11 to get rid of those two tildes and reach the conclusion. So let's go through this line by line. We started out by assuming that the conclusion was false, an assumption for indirect proof on line 2. But that gave us the negation of a universal statement. And from what you saw last week, you should immediately think that you can apply quantifier negation to that to move that negation inside the quantifier so you can start using the instantiation rules to get rid of the quantifiers. That's what I've done on line 3. I've moved this tilde from outside the universal quantifier to inside the universal quantifier, changing that quantifier from a universal quantifier to an existential quantifier. Once I have that existential statement on line 3, I can instantiate that with a constant. It just has to be a constant that doesn't already appear in the proof. There is no constant already in the proof. All I have are variables. So I can choose any instantial constant I want, lowercase a through lowercase w. I've just chosen m here arbitrarily. So I've dropped the quantifier and I've replaced those x's with a lowercase letter m. That gives me the negation of qm implies rm here on line 4. On line 5, what I've done is instantiate line 1, the universal statement, using that very same instantial letter. Now remember, you can instantiate universal statements either with a constant or with a variable. Here I've chosen the very same instantial letter m. That's what you see here on line 5. On line 6, I think you can see that I have the negation of the consequent of that conditional in line 5. So by modus tollens from lines 4 and 5, I know that the negation of the antecedent of the conditional in line 5 has to be true. And that gives me the negation of PM implies PM. And whenever you see the negation of a conditional like that, you should immediately think implication, because that will let you convert that conditional into a disjunction as long as you introduce a negation in front of the antecedent. And that will give you the negation of a disjunction and lead to a subsequent De Morgan's rule step. You can see that here a couple steps ahead. So what I've done on line 7, I've used implication on that conditional inside the parentheses. That gives me on line 7 the negation of not PM or PM. Applying De Morgan's rule on line 7 gives me not PM and not PM. That should be review at this point, just moving that tilde to both of those two terms, changing that wedge to a dot, for changing it from a disjunction to a conjunction between line 7 and 8. And then dropping the double negation on line 9 using the double negation rule will give me PM and not PM. That's what I'm looking for, a sum statement and the negation of that statement, an explicit contradiction. Then I can close off my indirect proof sequence. That's what I've done with that horizontal line between lines 9 and 10. That gives me the negation of our initial assumption. Then I just need to drop the double negation and we'll have the conclusion here on line 11. So pretty straightforward use of indirect proof. The key here, of course, is knowing what to do. If you're trying to prove something that you know you need, either the conclusion or some piece for an intermediate step, you assume the opposite of that. That's what we've done on line 2. Try to show that leads to an explicit contradiction. That could be any statement and its negation. It could be a simple statement like you see here, PM and not PM. It could be a universal statement and the negation of that same universal statement. Any statement and its contradiction counts just fine to close off an indirect proof sequence. And the rest should be pretty straightforward. It's indirect proof exactly as you've seen it up till now. Okay, I only have one more proof I want to look at. And like I said, we don't have much new this week. I want to give you time to do plenty of practice on your homework exercises. In this proof, we only have one premise. It's a fairly lengthy universal statement. For all x, if px or qx, then rx and sx. And we're trying to prove this conditional. If there exists something that's either a p or an s, then there exists something that is an s. If you notice in the conclusion, the main operator is that horseshoe. So this is essentially a conditional. So we're going to try to prove this using conditional proof. You can see on line 2 that what I've done, I'm going to circle it here. What I've done on line 2 is assume the antecedent of that conditional. So I can do conditional proof. So I cited at ACP, an assumption for conditional proof. Then what I'm trying to do, I'm trying to prove the consequent of that conditional. There exists something that's an S inside the scope of that indented sequence. Then I can close that off and reach my conclusion by conditional proof. So the question then becomes, how do I get there exists something that is an S? If I know I need that and I don't immediately see how to get started or immediately see how to get it, I can try to get that by indirect proof. That's what I've done on line 3. I've introduced a second indented sequence for the purpose of doing an indirect proof. If I know I need there exists something that's an S, I'm going to assume the opposite. So I'm going to circle that right here on line 3. That is the negation of that consequent that I know I need. There exists something that's an S. I'm doing that for indirect proof. So what I'm looking for now inside the scope of that second indented sequence is any explicit contradiction, some statement and its negation. And you can see right here on line 14, which I'm going to circle right now, I got that on line 14. Line 14 says A is an S and A is not an S. That's an explicit contradiction. Then I can close off my indirect proof sequence. That will give me there exists something that's an S after a double negation step there on line 15. And then I can close off my conditional proof sequence. So let's go through this now in a little more detail now that you see the broad brushstroke setup here. Like I said, I started out on line 2 by assuming the antecedent of the conditional that I know I need to get the conclusion. Then I know I recognize that I needed to get the consequent of that conditional. There exists something that's an S. So I introduce another indented sequence on line 3, the negation of what I know I need, trying to prove that for indirect proof. Hence, I cited assumption for indirect proof. Now I want to start applying my deduction rules, trying to get an explicit contradiction. So let's go ahead and dive in and let's just dissect this proof line by line. On line 3, we have the negation of an existential statement. And again, whenever you have the negation of a quantifier, you should immediately think quantifier negation to move that negation inside the quantifier so you can start applying your instantiation rules. That's what I've done on line 4. I've moved that tilde from outside the existential quantifier to inside the existential quantifier and changed the quantifier from an existential quantifier to a universal quantifier. That gives me on line 4 for all x, not sx. In other words, everything is not an S. Okay, from there, line 2 is an existential statement. So I instantiated that with a constant, keeping in mind that I have to use a new constant that doesn't already appear in the proof because it's existential instantiation. Here, we didn't have any constants at all in the proof, so I used the instantial letter A. That gave me on line 5. In fact, I'll circle these as we go. That gave me on line 5, PA or SA, which came from the existential statement on line 2 by existential instantiation. Now, line 4 is just a universal statement. It says for all x, not sx. And because that's a universal statement, I can instantiate that using any letter I want, any constant or any variable. Because I've already used the lowercase letter a, I'm instantiating that with the same letter, knowing that I'll probably have to apply some propositional logic rules in order to be able to actually use what I got on line 5. So that gave me not SA. I'm going to circle it right here on line 6. And that came from line 4 by universal instantiation. Now, this is pretty clearly a disjunctive syllogism step coming up. We have PA or SA. We know SA is false. In order to be able to use disjunctive syllogism, this should be really review for you guys at this point. The term that we have the negation of has to be on the left side of the disjunction. So I applied commutativity here on line 5 to reverse the order of that disjunction. So SA is on the left. From disjunctive syllogism, we know that PA then would have to be true because line 7 says SA is true or PA is true, and line 6 told us SA is false. That means we know PA has to be true. The next step that I did, I actually used addition on line 8 to give me PA or QA. And I did that, I'll circle it here so you can see what I did. I did that so when I instantiate line 1 using the lowercase letter a, which I'll circle right now, that will give me the antecedent of the conditional that I end up with. PA or QA implies RA and SA. That's just an instantiation of line 1. I took the universal statement in line 1, instantiated it with the same lowercase constant a, and I did that step on line 9, that addition step, so I would have the antecedent to that conditional on line number 10. That will let me do a modus ponens step because I have the antecedent of that conditional, so that will give me RA and SA by modus ponens right here on line 11, or on the top right part of the screen now. Well, I already know SA is false. That's what we have here on line 6. So the question then becomes, how can I get SA on its own line so I can, form my explicit contradiction, SA and not SA? Well, I already have SA here on line 11. I just need to get that on its own line, but I need to do commutativity first, so it's on the left side of that conjunction. That's what I did on line 12. I applied commutativity, so SA is on the left. Very simple step. Should be a review at this point. I simplified and got SA on its own line on line 13. And now I've got SA on line 13. Way back here on line 6, I've got not SA. So I can join those together. That gave me SA and not SA. There's our explicit contradiction on line 14. So that's what I was looking for. That allows me to close off our indirect proof sequence. I'll use a different color here. I know this is getting a little messy. That allows me to close off our indirect proof sequence inside this inner indented sequence, and that will give me the negation of our initial assumption. Our initial assumption on line 3 was it's not the case that there exists something that's an S. So we conclude the negation of that. It's not the case that it's not the case that there exists something that's an S. Not, there exists something that's an S. Of course, the double negations just cancel each other out. So that's what we did on line 16. We got rid of the double negations. That gave us what we were looking for, the consequent of that conditional that we started our conditional proof sequence for on line 2. Just for review, remember on line 2, we said that if we can assume the antecedent of the conditional that makes up the conclusion right here, which I'll circle in blue, which we did on line 2, and then if we can get the consequent of that conditional, there exists something that's an S on its own line inside the scope of that same indented conditional proof sequence, I could close off my conditional proof sequence, and that will give me my conclusion. And that's what I've done on line 17. This line 17 is just if there exists something, it's either a P or an S, then here's our conditional, of course, there exists something that's an S. And I got that from line 2 through 16 by conditional proof. So structurally, this should be reviewed. This is a great example of how you can use conditional proof and indirect proof in conjunction. If you know you need to prove a conditional, you can start out by assuming the antecedent inside the scope of an indented sequence, and then try to prove the consequent. But if you don't immediately see how to get that consequent, you can try to prove that consequent by indirect proof inside the scope of that initial conditional proof sequence. That's why I have two indented sequences, one inside the other here, and try to get the consequent by indirect proof, which I did here in this proof. So from here, there's really nothing new about conditional proof and indirect proof. Structurally, they're set up exactly the same way as they were in propositional logic. But again, just to reiterate this point, you have to keep in mind this rule, this restriction on the universal generalization rule, that you can't use universal generalization inside the scope of an indented sequence if the instantial variable that you're using to generalize is free or unbounded or isn't attached to a quantifier in the first line of that sequence. If you try to do that, that will result in something invalid, like you saw here in this sample proof with an invalid step. So again, I'm going to make this really explicit, like do not use this universal generalization in this way. That's an invalid step. That's all I have for you guys for today. You get some practice using conditional proof and indirect proof inside predicate logic proofs. If you find yourself stuck and you don't see how to do a setup for a particular proof, don't be shy about getting in touch with me. I'm happy to jump on a Zoom or answer your email and help get you started a little bit. But I think you'll see that conditional proof and indirect proof in predicate logic is very, very similar to the setup for propositional logic. It's just a matter of knowing what your initial assumptions should be and how to combine conditional proof and indirect proof and doing it strategically so you can apply whatever generalization rules it takes to prove the quantified statements that you're going to see as the conclusions of the arguments that you get. So again, if you're trying to prove a conditional, use conditional proof. If you know you need something, like after you've started your conditional proof sequence, if you know you need the consequent, try to get that consequent by an indirect proof sequence. Other than that, good luck on your exercises, and I hope you guys have a great week.